Welcome to the second part of Unit 7. In this set of examples, we are going to work two problems that both involve forces in two dimensions that we have to worry about. So the steps to solve these problems begin by drawing a picture and then determine what the problem is asking for, because depending on what the problem is asking for will determine how you organize things to draw your free body diagram. After that, draw any free body diagrams you need. You may need more than one. With your free body diagrams can include coordinate systems, label your forces in some means that make sense to you, include what direction you expect the acceleration to be in. If you need to, resolve any forces into components based upon your coordinate system. Then use Newton's second law in both directions, and if needed, solve your equations simultaneously. The first example involves a flea. So a flea jumps by exerting a force of 1.2 times 10 to the minus 5 newtons straight down on the ground. A breeze blowing on the flea parallel to the ground exerts a force of 0.5 times 10 to the minus 6 newtons. And we want to know the direction and magnitude of the acceleration of the flea given if its mass of 6 times 10 to the minus 7 kilograms. And it says specifically, do not neglect the fact that gravity acts on this flea. So first off, we're going to draw a picture. So we have a flea. Let's see. Oh, that's enough legs. A couple of antennae, pretty smile because it's a flea. Why not? We are told that flea exerts a force on the ground, and that force is 1.2 times 10 to the minus 5 newtons. We are told the flea's mass, so I'm going to make a little arrow here and just make sure that I know that the mass is 6 times 10 to the minus 7 kilograms. And we got a breeze, and that force from the wind on the flea has a value of 0.5 times 10 to the minus 6 newtons. And that's my picture. So from my picture, I'm now going to put that all onto a free body diagram, because what I want to know is what's going on with the flea. I've only got one object in this scenario. So we have the normal from the ground on the flea. And this one and this one we were given, the normal or the force from the flea on the ground and the ground on the flea, that's a third law force pair. So I can use the same magnitude there, 1.2 times 10 to the minus 5 newtons. There we go. We are told do not ignore weight, or gravity. So there we go. This is going to be the flea's mass multiplied by the acceleration due to gravity. And we will calculate that here shortly. And lastly, we have the force from the wind on the flea. And I don't exactly have enough room here to rewrite how big that is, so I'm going to leave the number off. I have my free body diagram. I need a coordinate system. Since I know I'm going to be accelerating upward and to the left, I'm going to let those be my positive directions and include the expected acceleration. Well, I just set it, so I'm going to draw it in and put those on as well. Okay, so I've got my free body diagram. I've got my coordinate system. I've got my expected directions of acceleration. So now I can apply Newton's second law in both directions. So in the x direction, F net x equals max. In the x direction, we only have one force, and that was from the wind or the breeze. I called it W for wind, and that has to equal max. So that force was 0.5 times 10 to the minus 6 newtons. The mass of the flea was given as 6 times 10 to the minus 7 kilograms. And dividing that out, we get an acceleration horizontally of 0.83, make that point a little bit bigger, meters per second squared. Similarly, I can do the y direction. In the y direction, I have two forces. I have the ground on the flea in the direction of the acceleration and the flea's weight in the other direction. So I'm going to take it as normal minus flea. Oh, normal minus flea. Let's try this again. Normal minus weight. The normal force had a value of 1.2 times 10 to the minus 5. Yes, 5 newtons. I've got to subtract off the weight. On the last slide, I made a mention that weight, remember, is always mass times the acceleration due to gravity as long as you're near the surface of the Earth. So that's 1.2 times 10 to the minus 5 newtons minus the mass of the flea, which is 6 times 10 to the minus 7 kilograms times 9.8 meters per second squared. And that has to equal, let's try again here. That has to equal 6 times 10 to the minus 7 kilograms times the vertical acceleration. Okay, so if you take and multiply 6 times 10 to the minus 7 kilograms times 9.8, subtract that number from 1.2 times 10 to the minus 5 newtons, and then divide the whole thing by 6 times 10 to the minus 7 kilograms, you get an acceleration of 10.2 meters per second squared in the vertical direction. Okay, now let's go back for a minute. It wants to know the magnitude and direction of the acceleration of the flea. Right now we have the components, which is not the same as having the magnitude and direction. So to get magnitude and direction, I draw myself a pretty triangle. I have horizontal acceleration, vertical acceleration, and the magnitude along the hypotenuse. I'm going to define this angle as theta. So now I can use Pythagorean theorem equals ax squared plus, let me try that again, ay squared, and if I plug in the 0.83 meters per second squared and the 10.2 meters per second squared, that results in the magnitude of the acceleration being 10.23 meters per second squared. And I can use tangent of the angle, which is going to be ay over ax, to determine that the angle is 85.3 degrees. And that concludes that example. In our next example, we are going to deal with a block sliding down a frictionless ramp. Okay, we're told the ramp makes an angle of 25 degrees with respect to the horizontal, and we want to know the block's acceleration. Okay, so draw a picture. Here's my ramp. Here is that 25-degree angle. Here is my block. And we know it's going to accelerate down the ramp. So the direction of the acceleration is going to be along the surface of the ramp, not up, not horizontal. And because that acceleration is pointed down the ramp, for this problem, it makes a whole lot of sense to align the coordinate system with the acceleration. So I'm going to tilt my coordinate system so that the vertical axis points perpendicular to the surface of the ramp and the horizontal axis points along the surface of the ramp. Now, with this definition for the coordinate system, the acceleration is strictly in the x direction. Okay, so now if I think about the forces on it, we have a normal force from the ramp on the block, which is perpendicular to the ramp. I've canted it a little bit to exaggerate the angle. And we're told it's a frictionless ramp, so the only other force acting on this block is its weight, which is gravity, which pulls downward straight towards the surface or center of the Earth. So that one isn't angled. And remember, my coordinate system aligns with the ramp. So my normal force is strictly in the y direction, but my weight force is not in x or in y. So I've got to define its coordinates. Let's try components. So the y component will follow the y-axis. So this is WEBY. And the x component will be parallel to the x-axis. So that is WEBX. There's my 90-degree angle. And what I really need to know is, what is this angle theta? Okay, this requires a little bit of geometry. And to get to that geometry, we have to draw a couple of triangles. The first triangle, I'm going to switch to blue, I guess, is I'm going to drop a line here that goes straight down. The weight force follows that line. And that gives me a triangle that goes like so. If this is 25 degrees, then that angle at the top must be 90 minus 25, which is 65 degrees. Okay. Now, let's switch colors again on you. Let's see, what haven't I used recently? Let's go with black. Now I have a right angle here, because the y-axis was by definition perpendicular to the surface, and I'm following the surface with the other piece. Because that's a right angle, and this is 65, that makes this little angle right here 25 degrees. And if you look, that little angle is between a up-down vertical and the perpendicular to the surface. So that's the same angle we have over here, which makes theta equal to 25 degrees. As I said, it required a little bit of geometry. With that definition, I can say WEBX is on the side opposite, so that will be WEB sine of 25 degrees. And that equals, if you put 4 kilograms, so remember this is going to be mg sine 25 degrees, so that's where the 4 kilograms came from. So 4 kilograms times 9.8 meters per second squared times the sine of 25 degrees. That all works out to be 16.6 newtons. I can also find the y component using a cosine, so WEB cosine of 25 degrees, which will be mg cosine of 25 degrees, which is 4 kilograms times 9.8 meters per second squared times the cosine of 25 degrees, and that equals 35.6 newtons. Okay, now that I have my components of my weight force, I can now apply Newton's second law in the 2 dimensions. So in the y direction, in our vertical, which really isn't vertical, it's counted to be perpendicular to the surface, we get the normal from the ramp on the block. Is that the same thing I used? And RB, yes, ramp on block, minus the y component of the weight force has to equal MAY, but it's not accelerating in the y direction. So this whole thing has to equal 0, which means the normal from the ramp on the block will equal WEBY, and that equals 35.6 newtons. Now, for this problem, we didn't actually need to find that normal force. It wanted to know the acceleration. However, I wanted to show you how to find that normal force, because shortly we're going to be doing a very, very similar problem involving a block on a ramp where there is friction. And when there is friction, that normal force becomes important. Getting back to this problem, it wanted to know the acceleration. Well, we set up our coordinate system so the acceleration was only in the x direction. There is only one force in the x direction, and that is the x component of the weight in this case. So that equals MAX. WEBX was 16.6 newtons. This is 4 kilograms times AX. And if you take 16.6 and divide by 4, you get the acceleration is going to be 4.15 meters per second squared. Let me fix that. Directed parallel to the surface of the ramp. This concludes this set of examples for Unit 7. We will work 2 more examples in the next part.